Hello, it's Ryan. This is our second example in one-dimensional motion. I wrote it out just to save us some time. So reads, an F-18 Hornet lands on a 100-meter landing strip with an initial velocity of 67 meters per second. If the Hornet comes to a complete stop at the end of the runway, determine the acceleration of the jet. So we're going to start this problem out the way we start any problem, and that's drawing a picture. So we'll draw a picture. Start with our runway. There it is. We're given that the runway is 100 meters long and that the jet's going to land. So we'll have the jet just the instant it lands. Here it is. Wheels might be a little too close together, but that's okay. There's the wing and the other wing. There it is. So we can actually put the other wheel back here. Now this is not a great jet, but I never promised to be good at drawing. We know that this jet is going to land with some initial velocity, v sub o. We can also show that it's going to land, and we'll probably say that its initial position is here, and where it comes to rest, its final position is there. When we say something comes to a complete stop or comes to rest, we're telling you that the final velocity is, of course, 0. So this is where our jet will end up. There it is. So we could note that we have a final velocity here of 0. And we usually don't put the numbers in there, but that's okay. We have a displacement then, like so. And now we have an acceleration again. We know because the velocity is changing, it's going from some v sub o to some 0 velocity, right? We know the v sub o is 67 meters per second. And so the velocity is changing. And in what direction is the velocity changing? To the right or to the left? If it were changing to the right, we know that the velocity vector would be increasing. And we know that it's not. In this case, the velocity vector is decreasing, so the acceleration must be to the left. And we'll label that with an A and a vector symbol. That is our acceleration. But that makes sense. The velocity vector is slowing down. The velocity of the plane is slowing down, and we know that that means that it must be changing to the left in that direction. This means that we're now not only going in one dimension to the right, but we also have to keep account of quantities that may be pointed to the left. And the way we can do that in math, of course, is by indicating a positive direction here. And so the way I'm going to do that is I'm going to just say that this runway is like our x-axis in meters. And so anything pointed to the left will now be in the negative direction. This is not a bad picture, not artistically, but it has everything we need. And so we can now put our knowns and unknowns. We know that v sub o is 67 meters per second in the x direction. We know that the displacement is 100 meters in the x direction. I'm just writing these as vectors just to remind myself that they're vectors. Really maybe isn't necessary, but why not? We know that the final velocity of our plane is 0. I never really write units on zeros. 0 meters per second is the same as 0 meters, and it's the same as 0 kilograms. 0 times anything is 0, of course. So it's really one of the only places I won't write my units on. We're looking to find A. And I don't think we know the time either. And now, just because we don't know the time, I'm putting it in there in case that helps us pick an equation later. So we've kind of completed our setup to solve the problem. We need a picture and to remind ourselves of the knowns and unknowns. And again, the thing that helps us the most with is not having to reread the problem over and over. So now we know we're looking for A. We want to determine A. And in order to do that, we should use the big three. So let's just remind ourselves what the big three are. Just write them down real quick. There they are. We know going into this that V is 0 at our T final. We also could probably say that S initial is 0. We might as well start this out at 0 and have it go to 100, which means S final is 100. Maybe not necessary, but I just want you to see everything that we need to think about while we're solving this. So we know we're looking for A. Oops. And we know that we also don't know T. So I just underlined our unknowns, and in fact, I could do this. Here's our unknowns. And so really there's multiple ways to solve this. If you notice, we have two equations and two unknowns. So we could use both of those and then solve the problem for A. What we would do is we would solve this for T, and we would substitute it in to there. Or we could just take the equation with one unknown. So I think we'll do that. So we'll just can also input that our final velocity at the final displacement will be 0. So we could put in a 0 here. So we've got 0 equals 2a delta s plus v sub o squared. And now we can solve for a. I'm going to subtract v sub o squared by both sides, and then divide both sides by 2 delta s. So we'll end up with a equals negative v sub o squared over 2 delta s. And just to keep going with this rigorous solving of the problem, I'm going to go ahead and just break up the delta. So that would be S final minus S initial. Now we can substitute our values. So we have negative, and the negative's outside of the parenthesis because the square and the negative are independent operations on v sub o. So we have v sub o was 67 meters per second squared divided by 2 times, and it's 100 meters minus 0. So we'll end up getting A equal, and we'll get negative because of the negative sign, 22.5 meters per second squared. And this is in the x direction, just like our picture gave us, and just like it really had to be to slow the plane down. Another way to write this, we could, don't forget your vector symbol, we could write A equals 22.5 meters per second squared, and then we could note that it's in the negative x direction. That would be a completely acceptable answer. We give both magnitude and direction. Another way we could write this, A equals 22.5 meters per second squared at 180 degrees. All these are acceptable. Choose whichever you like best. If you have to give a vector equation, make sure you give the magnitude and direction. So that's our second linear motion example. This time we had a negative acceleration. We had something slowing down. Oftentimes people would say that it decelerated. That's probably the first and last time I'll use that word in our class. Accelerations can be positive, they can be negative. The important thing is that they have direction, and as long as you pay attention to both direction and amount, you can't go wrong. So there's no reason for the D word. Anyway, thanks for watching. Good luck. Talk to you soon.